So let us now understand what actually is a quantum phase space. We already saw what a classical phase space is in earlier videos. So a quantum phase space is a way to visualize states in the continuous variable quantum computing paradigm and how various operations change these states that can be visualized using the quantum phase space. It serves a similar purpose that a Bloch sphere serves for the discrete variable quantum computing. So, quantum phase space, like classical phase space, is formed by having expectation values of position of a state on the x axis and expectation value of momentum of a state on the y axis. Unlike in the classical case where we have a point representing a state of the particle, we have here what is called as a Wigner function instead. A Wigner function is a quasi-probability distribution function and acts just like a probability distribution function of a quantum particle. But there are a few things which are different from those probability distribution functions when it comes to Wigner quasi-probability distribution function. So if I want to show this pictorially, the classical phase space, if you recall, is given of a single particle is given by something like this. A single particle on a one-dimensional space. So we have x-axis on the position on the x-axis and momentum on the y-axis, and the particular state of the particle which is given by the position and momentum, is given by a point in this classical phase space. If you recall, we had spoken about the classical phase space of a harmonic oscillator, and as it evolves, this traces a circular path on the classical phase space. In the same way, if we are trying to visualize a quantum state of a quantum particle on a class quantum phase space, the x-axis represents expectation value of position of the state, and the y-axis represents expectation value of the momentum of a state. And as I told you, that unlike this being a point, it is represented by a Wigner distribution function, and hence there is a spread. So the particle is given by a Wigner distribution function. Particle state is given by a Wigner distribution function, and there is some non-zero uncertainty which is there. So this is Wigner, and this is just a point. And these spread, it gives you an idea of the uncertainty in the position and momentum of that particular particle in that particular state. So this is a very general overview of the quantum phase space. So before going ahead, we will derive the expectation values and the uncertainties in particular states in general. The states that we will cover for now are the Fock states and the coherent state. And I will show you how you can visualize them on the quantum phase space. In the later parts of the videos of this series, we will look at how the squeezed state can be represented on the quantum phase space. But for now, we will just focus on these two. So first we will calculate the expectation and uncertainties in general, and then we will all in the next video look at how those Wigner functions for these two types of states look like and their mathematical expression. So let's start with calculations of the expectations and uncertainty of the coherent state. Let us first calculate the expectation value of the position operator for the coherent state. Mathematically, it is expressed as this alpha x cap alpha. So let us calculate it. Now x cap is given by h bar by 2 a cap plus a cap dagger. So alpha x cap alpha is equal to root of h bar by 2 alpha a cap plus a cap dagger alpha. Now, as this is a number, we can take it out, and these relations we have covered in previous videos. H bar by 2 alpha a cap alpha plus alpha a cap dagger alpha. Now you recall earlier what a cap acting on alpha gives us. A cap acting on alpha gives us alpha because alpha is a eigenstate of a cap. So this becomes alpha alpha plus a dagger acting on alpha on the left hand side will give me alpha star alpha alpha. This is equal to saying that this is a cap alpha whole dagger. So this is equal to alpha alpha whole dagger equal to alpha star alpha. So that is what we have done here. So as the coherent states, if the coherent states are normalized, you should recall that coherent states are not orthogonal. But we are considering our normalized coherent states, so this has to be equal to 1, both of these. So this is equal to alpha plus alpha star. So this is what alpha x cap alpha is equal to. I can give it a notation something like this alpha, the expectation value of the position quadrature. Now let us calculate the expectation value of the momentum quadrature. So we know that p cap is equal to minus I h bar root of h bar by 2 a cap minus a cap dagger. Now you should be aware that there are different conventions. So you can take h bar equal to 1, 2, etc. You will get different answers. But the point is, at the end of the day, the answers that you will get will be some multiple times what is the exact quantity. So the quality wise it won't differ much, except there will be some constant which will be multiplied. So pardon me if I am not having a proper streamline with the kind of assumptions that were taken in previous lectures. So alpha p cap alpha is equal to minus I h bar I into root of h bar by 2 alpha a cap minus a cap dagger alpha, and this is equal to minus I h I root of h bar by 2 alpha a cap alpha minus alpha a cap dagger alpha. Just the way we did it earlier, this is equal to minus I root of h bar by 2 alpha minus alpha star. Okay, so this thing is equal to, as this is alpha plus alpha star, this is equal to 2 times real part of alpha, right? And this will be equal to minus I times alpha minus alpha star is equal to 2 times imaginary part of alpha. So your p cap expectation value is equal to root of h bar by 2, 2 times imaginary part of alpha. Now you'll understand the importance of what all we are doing here once I will show you visually on the quantum phase space how these states can be represented. Now let us try to calculate the uncertainties. For the uncertainty, we will need to find the expectation value of x cap squared operator. So let me try to calculate it. So this is equal to h bar by 2 alpha a dagger a plus a dagger into alpha. So I just explicitly wrote x cap here. So if I open this up, this is equal to AA plus AA dagger plus A dagger A plus A dagger, this entire thing. So let me now write it down. Alpha AA alpha plus alpha AA dagger alpha plus alpha A dagger A alpha plus alpha A dagger alpha. Now what this will do is it will give me, if I act this once and then I act it twice on alpha, this should give me alpha square. Yes. Now this thing can be written as using the commutator relation a dagger equal to 1. This a dagger a is equal to a dagger minus 1. So a dagger, just a minute. Oh, sorry. A dagger is equal to a dagger a plus 1. So let me just write down each term one by one. So when this will act, this can be replaced here. Let me write it down properly. It will be better. Alpha a dagger a alpha plus, and this when it acts both of these on the left hand side, this will give me a star square, and alpha a dagger a alpha is equal to mod of alpha square, because this will act on here and this will act here, so it will give me mod of alpha square. This will give me a star, this will give me this will give me alpha star, this will give me alpha, so this is alpha star, mod of alpha star square. So this is mod of alpha star square, and this is mod of alpha star square plus 1. So in entirety, this will become mod of alpha star square plus 1 plus mod of alpha square plus alpha star square. This is what we will get. Now I can write this as alpha plus alpha star square plus 1. So this is x cap square alpha. This is the value of expectation value of x cap square operator for the alpha state. Now, similarly, I'll not calculate it. I'll leave it on you. You have to follow the same procedure. You can prove that alpha p cap square alpha equal to p cap square alpha is equal to minus h bar by 2 alpha minus alpha star square minus 1. This is what you will get. So now let us calculate the uncertainty in the position for the coherent states. So the uncertainty or the variance in the position of the coherent states is given by this value. Now this and this first and the second term we have already calculated earlier. So let us write them down over here. So this is equal to h bar by 2 alpha plus alpha star square plus 1 minus h bar by 2 alpha plus alpha star square. Now, if you open this up and you will see that this and this will cancel, and the value of the uncertainty is equal to h bar by 2, or the variance is h bar by 2. Similarly, this is the variance of the momentum operator for the coherent states. So this is equal to minus h bar by 2 alpha minus alpha star squared minus 1 uh, let me just check, minus of h bar by 2 alpha plus alpha star, or sorry, let me just check, wait a minute. This is minus h bar by 2 alpha minus alpha star square minus 1, and p cap expectation value squared is this. So minus minus plus minus h bar by 2 alpha minus alpha star square. Yes, there will be a minus sign here. So minus minus, just a minute. Okay, there is a minus, and then so this will become plus, and this will get cancelled, and this minus and minus will give me h bar by 2. So this is the uncertainty in the momentum operator for the coherent states. Now, if you want to calculate the product delta x into delta p, we will see that it is equal to h bar by 2 under root into h bar by 2 under root, because the square here was equal to h bar by 2, so this is root of that. Let's put an alpha over here. So this is equal to h bar by 2. So delta x alpha delta p alpha equal to h bar by 2. Now, this is according to the uncertainty principle, Heisenberg's uncertainty principle. This is the minimum uncertainty that can be reached. So we see that current states are minimum uncertainty states. Now, let us calculate the uncertainty. Let us calculate the expectation values and uncertainties for the Fock states. So, the expectation value of the position for the Fock state or the number state or in a single mode is given as this particular quantity. This is x. And let us calculate it by explicitly noting down the position quadrature operator. So this is equal to a cap plus a cap dagger n. And this is what you get: root of n into n minus 1 plus root of n plus 1 n plus 1. We take note that a acting on n is equal to root of n into n minus 1, and a dagger acting on n is equal to root of n plus 1 into n plus 1. So that is what we have used here. So this is equal to root of h bar by 2 into root of n into n minus 1 plus root of n plus 1 and n plus 1. Now, using the orthogonality relations, this and this is equal to 0. So, x cap and expectation value of x cap for position operate for the Fock, single mode Fock states is equal to 0. Similarly, we can prove that this is also equal to 0. I leave it on you to prove, as it is very easy to prove it. Now, n into x cap square n, the expectation value of x cap square for the um, single mode Fock states, or the Fock state, I would say, is root of h bar by 2 n into a plus a dagger a plus a dagger plus a dagger into n. Recall that we have used the definition of x cap here, and we just expanded it just as we did it earlier for the coherent states. So this will turn out to be equal to n into root of n into root of n minus 1 n minus 2 plus root of n plus 1 square into n plus 1 minus 1 plus root of n into n minus 1 plus 1 plus root of n plus 1 into root of n plus 1 into n plus 1 plus 1. I've just operated these and used the definitions of the creation and annihilation operators. And at the end of the day, using the orthogonality relations with this n and n minus 1, and this will be equal to n, this will be equal to n, and this will be equal to n plus 2. So only this second and third terms will survive, and you will get this to be um, you will get this to be equal to uh, h bar by 2. Sorry, this will be equal to square because it is x cap square, uh, and this will become n plus 1 plus n. So this is h bar by h bar into n plus half. This is what um, x cap square for the Fock state will look like. Expectation value of x cap square for Fock state. So this is 10. 11th, we will use the same procedure as above. I will again not derive it. I leave it on you to derive. And at the end of the day, we will get this also to be equal to n plus h bar into n plus half. Now let us calculate the variances. So This is equal to x cap square n minus x cap n whole square. So this will be equal to um, 2 h bar into n plus half minus 0, because this was equal to 0. So this is minus 0. So this is equal to h bar plus h bar into n plus half. Similarly, delta pn square is p cap square n minus p cap square n, which is equal to h bar into n plus half minus 0, and hence at the end of the day this is also equal to h bar into n plus half. And the product delta x n into delta pn is equal to root of h bar by 2 into n plus half into root of h bar by 2 into n plus half, and this is equal to h bar by 2 into n plus half. So you see that for vacuum state delta x and delta x delta p, this is 0, let's say n equal to 0, is equal to h bar by 2. Sorry, there is no 2 here, because n is equal to 0, so this becomes h bar by 2. For n equal to 1, delta x 1 delta p1 is equal to uh, 3h bar by 2, and so on. Okay, so now that we have derived all these things, all these relations, let us try to visualize whatever we have understood. Visualize whatever we have learned until now on the quantum phase space. If I summarize our derivations of the expectation values and uncertainties, this is how they look like. Now, let us try to visualize the where the vacuum state can be represented on the quantum phase space. So the quantum phase space, if you recall, I had said that the x-axis represents the expectation value of the position and y-axis represents the expectation value of the momentum. So the vacuum state will lie on the origin of this space, the quantum phase space. And I can represent the uncertainties by a, let's say I represent it by a circle. In reality, it's a Wigner function, which I will come to in later videos. But for now, let's just say that it is represented by this circle on the origin, and the spread of this circle is equal to 2 times delta p in the y direction and 2 times delta x in the x direction. So we had already derived these uncertainties here, and so if I look at it, it will be equal to so delta x 0 will be equal to root of h bar by 2 into 2. So this will be equal to 2 times root of h bar by 2, the spread here, and this will be equal to root of 2 into of h bar by 2 in the x direction. So the vacuum state will be represented by this particular circle. And here this is delta x cap 0 equal to 0 and delta p cap 0 is equal to 0. Now let us represent the coherent state. So the coherent state will be centered somewhere on the away from the origin, any general coherent state. And again, the spread will be given by a blob of an equal size as that of the vacuum state. The position of this particular, the center, is directly proportional to the real part of alpha, as we saw here, and the position in the on the y-axis is directly proportional to the imaginary part of alpha. And that way, the direct distance from the origin of this center is directly proportional to mod of alpha, where alpha is equal to mod of alpha e raised to I theta. Yes, x cap alpha, and this is p cap alpha, expectation value. So this angle, you can say that it is equal to theta, and this is mod of alpha, just like how we do it in the complex plane. The spread here again is the same as that of the vacuum state, 2 times delta p alpha, so it is equal to root of 2 into root of h bar by 2, and here it is equal to 2 times delta x alpha, which is 2 times root of h bar by 2. There can be some uh, discrepancies in the constants, forgive me for that, but quantitatively or qualitatively the sizes are same, and the distances are proportional to what I have mentioned here. Okay. One more thing that needs to be noted down is that this is also equal to mod of alpha sine theta, and this is equal to mod of alpha cos theta. It is just because this is equal to mod of alpha cos theta plus I mod of alpha sine theta. So this is what we are using here. So this we can write this also as equal to root 2 h bar mod of alpha cos theta, and this as root 2 h bar mod of alpha sine theta. Okay. Now the higher order states, the Fock states will also be centered at the origin by these relations. By these relations, however, the spread will differ as n goes above 0. So the spread will be higher and higher for the higher order Fock states, single mode Fock states. So this is how we can visualize them without the Wigner functions, the positions. Now, if I do operations like squeezing, which we will come to at the later part, we will see that these circles will get squeezed in a particular direction according to the squeezing operation applied. However, the area of this squeezed circles will be the same as the this particular circle, according because of the Heisenberg uncertainty principle. There is something called as the rotation operator, which will rotate the center around the origin. So that is called as a rotation gate, and there are many other gates which are there, which we can operate on these coherent states, Fock states, squeezed states, and we can visualize them on the quantum phase space. So in the next video, we will come to the derivations of the Wigner's functions for these different states, and also then try to visualize